and the big picture. So the gas turbine has been around, and jet engine has been around for almost 9 decades. And up to this point, the gains in jet engine thermodynamic efficiency gains are largely driven by increases in turbine inlet temperatures, or TIT, and which is accompanied by increasing overall pressure ratio. So I'll give you an example for the latest, the biggest engine, G9X engine. It has a TIT about 1800 Kelvin, and to reach the peak thermodynamic efficiency, it needs a 60-to-1 pressure ratio. All right. Now, so what is TIT? So there's a difference between T-flame and the TIT. If you look at this cross-section of a gas turbine combustor, TIT essentially is the gas temperature goes into the turbine, and whereas for the temperature in the combustor essentially is the T-flame or T5. And T5 is not exactly the same as the TIT because the flame temperature, the combustion products needs to mix with cooling air, and then becomes the gas, the bulk of the gas to drive turbines. So TIT essentially is something between the T-flame and cooling air. So cooling air is very expensive because it has to go through all those stages of compressors to be used for cooling. And roughly about 1/3 of the compressor discharge air is used for cooling and for profiling. So all those air has to be taken out from the compressor, and they're very expensive. And because we use cooling air, TIT is actually lower than the T-flame temperature. So as a result of the mixing with the cooling air. So from a thermodynamic perspective, we want a high TIT to get a high efficiency. Then the question is, why can't we just go ahead and increase the T5 or T-flame? Well, the answer is that the T5 essentially is limited by emission standards. We really cannot increase T-flame too much because essentially, particularly the NOx emission is set by Cap A right now. And as you can see, most of the modern engines, they barely meet the emission standards for NOx emissions. So that basically says it's very hard to increase T5 anymore. And if we want to increase TIT, and also we want to reduce the cooling air usage, it makes most sense to increase efficiency. It makes most sense to reduce the cooling air usage. And another aspect from a cooling perspective is that if we look at the big picture, there are a couple of numbers I want to introduce. Well, first of all, the flame temperature is about 2,000 Kelvin or a little bit higher. And even the latest super alloy limits at 1,400 Kelvin. And if we're talking about a 60-to-1 compression ratio, even the cooling air is at 1,000 Kelvin. So that doesn't really leave us too much space for doing the cooling, and really makes cooling very expensive and important. The rule of thumb is that for every 1% reduction in cooling air usage, you probably can get 0.5% improvement in the overall engine efficiency. So there's huge benefits in making the cooling more efficient and use less cooling air, and so that the overall engine can be more efficient. Another aspect of the cooling is that the longevity of engine living is mostly dependent on cooling. So our goal is to reduce cooling air consumption through improved thermal management for gas turbine combustors. As the state of the art, efficient cooling, that's the state of the art. And what is efficient cooling? Well, here I have a picture of what's happening inside an aero engine. You can see all those tiny holes. They are aligned with the axis of the combustor. They're essentially efficient cooling holes. And for the efficient holes to work, essentially you have the cooling air flowing on the backside of the combustion liner, and the cooling air passing through all those tiny holes, and gradually forms a cooling film over the hotter side of the liner, and that is cooling film that protects the metal surfaces from the hotter combustion products. And we can usually use CFE cooling film effectiveness to quantify cooling film the efficiency or the effectiveness of cooling film. And essentially that is a ratio of two temperature differences. The one in the denominator is a temperature difference between the burned gases and the wall temperature. And what in the numerator is the temperature difference between the burner gas and the cooling air. So that's how we define the CFE. One thing I want to point out is that the wall temperature and as well as CFE, they are localized. And for a gas turbine combustor perspective, essentially is the lowest point of CFE determines the amount of cooling air that we have to use, or determines the life of combustion liner. Because if there was one spot that gets over temperature, and the entire liner will have a shortened life, right? So CFE is determined by the least effective spot, and the goal, again, not only we want to reduce the cooling air usage, also we want to make the cooling film as uniform as possible, so that there's essentially no weak points in the combustion liner. A quick view of the experiment setup, and I probably won't dive into all those details, but one thing I want to point out is that we actually use heat mass transfer analogy in measuring CFE, the cooling film effectiveness, because in this setup, we want to essentially the coolant will separate the liner from the main combustion gas. And so that essentially is the cooling film effectiveness. But if we measure let's say if we use a coolant that doesn't have oxygen components, and if we measure the oxygen components near wall, then we can get an idea of how effective the cooling film is. And this is the definition of we can calculate the CFE from the partial pressure measurements near the wall. And the method we making those measurements is we use something called PSP, pressure sensitive paint. And the PSP is sensitive to the partial pressure of oxygen near the walls. So the first thing we want to look at from a effusion cooling perspective is that all the modern aero engines, it has a swirling combustor, meaning that the main combustion products, they are swirling inside the combustor. And but if you look at those effusion cooling holes, they are essentially collinear with the axis of the combustor. So then we have an offset angle or compound angle beta. And for most of the engine designs, they assume that the effusion cooling just go collinear with the combustor. And so we want to say, how good is that assumption, given that the main combustion products, they are swirling inside the combustor. So we come up with an experiment setup. Then the baseline case essentially is all the effusion cooling holes, they are collinear with the combustor, and then we make the change the compound angle going from 0 to 30 degrees, 60 degrees, and 90 degrees, and we want to say, well, what would be the best compound angle for effusion cooling. And given that the flame is swirling inside the combustor, how far off are we from this optimal compound angle? And we performed a set of experiments, and as you can see here, so first of all, let me introduce to how we read those diagrams. Well, the red essentially is the hotter part, if you think. And the blue side is actually anything that's more blue essentially is cooler. So what we want, our ideal situation is that we use cooling air to remove all those red, deep red parts on the cooper, and we're trying to get something as uniform as possible on the surface to be light color or even more blue. So what we learned from this simple experiment is that the offset or component of efficient, the component angle, optimal component for efficient cooling is somewhere between 30 and 60 degrees, which is actually a great news for existing jet engines because for the typical swan number of 0.7, the compound angle happens to be around 45 degrees, which is between these two optimal angles we found. So far the jet engine business have been doing very well. And then we dig in a little bit deeper and say, well, depending on at what stage of the efficient cooling film development, different offset angle could be of different effectiveness. And we identify that at the onset of efficient cooling film, a big component angle actually is more efficient. And then as the cooling film develops, slightly reduced component angle works best. And then towards the downstream, when the cooling film is fully developed, we can reduce the component angle to about 30 degrees. And with that understanding, and here essentially is, our understanding is that the cooling film effectiveness is a delicate balance between how deep the cooling jet, efficient jet can penetrate, and versus it mixed with the main flow. And we come up with a design that has a varying component angle. And essentially we have two different designs. One is a three discrete component angles, and the other one is actually continuously varying component angles. And we anticipate this continuous varying design will be slightly outperform the other design. And we did a test, and indeed it was, as you can see, those the fixed constant offset angle, component angle, and these two designs are varying component angle. As you can see, the new design is outperform the constant design. Well, the benefits here essentially is between these two is about 3%, not much. But if we compare to the baseline case, it's about a 46% enhancement to the baseline case. It's about 10% enhancement to the optimal case by the 60 degrees. Another thing we learned from our study is that the cooling film takes time to develop. So for a conventional efficient cooling design, we essentially have a uniform distributed efficient cooling holes, and the drawback is it's clear because we said the weakest point on the cooling film determines the effectiveness of the whole cooling film. But if for a conventional design, as you can see, the leading edge, there's not enough protection from the cooling film, and it takes some time for cooling film to develop. So our idea is that we probably need to redistribute all those efficient cooling holes. So at the leading edge, we can make the cooling film to develop as quick as possible. But once the cooling film is developed, we don't really need that much of a cooling film air to maintain it. So we can gradually reduce the amount of cooling holes or cooling air usage towards the trailing edge. So demonstrate. We designed another set of more comprehensive experiments, and we changed the component angle with the same ratio of reduction in cooling film, cooling hole distribution. And we can see that redistributed cooling holes can be pretty robust and have a uniform enhancement of cooling film effectiveness. So if we compare with the baseline case, we can say roughly, very robustly, we can have about 2 times enhancement of cooling film effectiveness based on the same efficient cooling technology. So the next step, I think we can talk about the future of cooling from our understanding. Our understanding is that the transpiration cooling can be a game changer for enhancing cooling because there are multiple benefits from transpiration cooling. One is it can allow a high flow rates, provide more effective cooling, and the efficient cooling, transpiration cooling are more distributed. So they are potentially, or they inherently will be more uniform. The big picture is also that the advanced transpiration cooling is enabled by recent advancements in additive manufacturing. So a lot of advanced transpiration cooling design that is not possible in the past, but now it's all becomes possible with additive manufacturing. And we are looking at this, here I'm not going to name those lattice structures, but those are particularly engineered lattice structures, and we actually found them have very good mechanical properties, have very good thermal aerothermal properties, and that's what we are using for our transpiration cooling studies. And here are some early results, and it's already the benefits can be very clear here. So on the top panel, they are all traditional effusion cooling, and on the bottom panel, they are transpiration cooling with our additively manufactured test coupon for a uniquely designed lattice structure. And if we do the average of the CFE over different columns or over different rows, we can say that the improvement is over the entire test areas, or more than 4 times in enhancement in CFE. So just maybe to highlight a couple of the benefits of transpiration cooling, it's apparently it's more uniform film coverage. It enables the cooling film to remain stable and attached to the wall even at very large flow ratios. It offers a more efficient internal wall cooling throughout forced convection. So a lot of benefits of doing this type of transpiration cooling. So let me just, I think my time is running out. Let me just conclude what we just discussed. There are greater potentials for improved gas turbine efficiency through reductions in cooling air use. If we focus on effusion cooling, there's about 2 times enhancement potential can be achieved in CFE just by optimizing what we already have, the effusion cooling. But if we move to a different technology, transpiration cooling, the cooling fuel effectiveness we can have at least 4 times enhancement. The future work focusing at transpiration cooling will be investigating durability of this new technology. Particularly, we'll be looking at the mechanical stress, the fatigue, and the contamination and such. With that, I'm going to wrap up my talk.
All right. Thank you very much, Zekai. I guess we have time for a quick question if there's any questions from the audience.
If there isn't one, I just have a quick question. So it's very interesting, Zekai. I actually work on the material side of this problem, like increasing the temperature capability of the materials to reduce the cooling usage. I just had a quick question about your modeling. Really great work. So I see that you're modeling on, flat panels with the varying component angle. I was just wondering if you're planning on doing modeling on more curved geometries like you would expect on turbine blades or vanes.
So first of all, I probably didn't make it clear. Those are not modeling works. Those are actually experimental measurements. We actually designed a coupon, built a fabricated coupon, and we put them in those test stands, and we actually did the measurements. So the benefits, they are real and they are measured. And yes, we do actually have some numerical simulation work in parallel. For the sake of time, I didn't present those numerical validations, but yes, those are in parallel. And as to your second half of your question, use them for turbine blades. I think it's very interesting. It's also very challenging because turbine blade is probably under higher compound stress between thermal stress and mechanical stress. So it probably makes a lot of sense if we can validate this technology, particularly transpiration cooling, and we probably can transplant that to turbine blades.
All right, awesome. Thank you.
Thank you.
So we'll bring in our next speaker, Dr. Jacob Gissinger from NASA's Langley Research Center in Hampton, Virginia, and he's going to give a talk on predicting the char yield of high temperature resins.
Thank you very much for that introduction. I'm Jake. I'm currently in my third and final year of postdoc here at NASA Langley Research Center. And today I'd like to talk about some of the computational modeling work that I've been doing over the past couple of years related to predicting how polymers behave when subjected to extremely high temperatures. So why is this of interest to NASA? Well, these are the types of materials that would go on the outside of a spacecraft to act as a thermal protection system or heat shield as it's re-entering the atmosphere. So you may be aware that there was a successful uncrewed mission around the moon late last year called Artemis 1 from NASA. And here's an illustration of the Orion capsule as it's re-entering the atmosphere. The job of the heat shield is to protect it from the extreme temperatures that it is subjected to, which are upwards of 3,000 degrees Kelvin, so about as hot as it gets. And the heat shield on our Orion capsule behaved well overall, above expectations. However, there were some unexpected small behaviors, such as very small parts kind of breaking off as opposed to a uniform ablation of the entire heat shield surface. So that's something that wasn't predicted by the large-scale ablation models that the NASA engineers had. So that's something they're working to correct. I don't work on large-scale ablation models. I work on the atomistic scale, but there's something to keep in mind as we now delve into much lower length scales. So first of all, what is char yield and why is it important? Char yield is simply the amount of material that's left over after you subject it to extremely high temperatures. So in experiment, this is measured by a technique called thermogravimetric analysis, or TGA. And this is a way to simultaneously weigh the material and subject it to extremely high temperatures. So the result is something like this graph, this plot that you see down here, where you see a mass loss as volatile gases are being vaporized and removed from the material. And it is important for materials processing, for example, for carbon-carbon composites, because the way they are made is you take a carbon fiber, a woven fabric, you infiltrate it with a resin, subject that to extremely high temperatures, which causes pores to form as these volatile gases are released. You then put more resin into those pores and resubject it to those high temperatures and repeat that process until you achieve your desired density and properties. So high char yield materials are able to require fewer cycles to reach this target density and property that you're looking for. So before this work, there was really no way to predict this important value of char yield in a predictive way, in a chemistry-specific way, and in a way that didn't require interpolation of data from the literature. So this is a predictive method, and here's an overview of the simulation protocol that I came up with. It's actually, follows a similar pattern as a material might experience during experiment. So you start here at room temperature, ramp it up slowly to this annealing temperature, and hold it there for a while. A couple important points during this annealing stage is I'm subjecting it to high pressures in order to achieve the densification and kind of the chemical rearrangement that we would expect. And at the same time, also very importantly, we are removing these small volatile gases from the simulation box occasionally. So typically in experiment, of course, these would be able to diffuse out during the length scales accessible by atomistic simulations. We simply remove these after a certain amount of time. And this again allows for the chemical rearrangement and densification of the material that we would expect at these high temperatures. And then we bring the material back down to room temperature and can do some further analysis on it from there. So let's jump into some results. First of all, the chemistries that we looked at are all along this bottom left here. So you can see that there's a wide variety of different chemical groups on all these molecules, a different percentage of heteroatoms, which are the non-carbon atoms in these resin chemistries, as well as different amounts of aromatic carbons or carbons involved in these rings. So all of these factors play a role in deciding what is the char yield for a given material. And on the right, you can see the results, which are very nice correlation between the simulation expected values, and it follows the same trend with our predicted values from simulation. So this is a promising sign that this method is able to predict the important value of char yield without having to interpolate data from the literature. So the target density for all these materials was between 1.8 and 2 grams per centimeter cubed, as was taken from experiment for the resin phase of a carbon-carbon composite. And there was really no correlation between density and char yield. However, as expected, a very strong correlation between the mechanical properties and the density. So here I'm showing the Young's modulus, the elastic modulus of the material. We also looked at the ultimate strength of these materials as well. And in both cases, they were over-predicted by our models, but that is not too surprising because the model that we end up with is essentially has no defects and no large porosity. So one of the things we're looking at is how to couple these types of atomistic simulations with larger scale models that can include large pores and large defects, which play a very important role, of course, in the ultimate strength and other mechanical properties of your material. But let's take a look at what these atomistic models actually look like after going through that whole temperature cycle. So here's a couple examples. On the right here is for a high char yield resin. What I'm showing here is just the carbon rings left over, which makes up the vast majority of the material. So I'm showing the 5, 6, and 7-membered rings. There's a couple interesting things to note. There are about twice as many 6-membered rings as 5 or 7-membered rings. And also the 6-membered rings are well distributed throughout the network, as you can see. So this is kind of characteristic of amorphous glassy carbons. On the inset down here is a lower char yield material. And qualitatively, you can see that it looks pretty similar, and actually quantitatively as well, you get the same ratio between the number of rings between these two materials. So it's a sign that despite different initial chemistries and different char yields, they kind of converge in the same pretty messy glassy carbon structure. So let's look at a couple ways to directly compare these simulation results with experiment. One way is to keep track of the volatile gases that are being released. On the right here, you can see the volatile gases that are being deleted from the system with respect to each type of chemistry. And the main takeaway here is that they largely agree with what is seen in experiment, which is a good sign that we're getting the chemical physics correct for this model. There were a couple of disparities, though. For example, we are overpredicting the amount of carbon monoxide versus carbon dioxide that's released from these types of materials. And that can be attributed to the fact that we're kind of removing the carbon monoxide too quickly before it can wander around, find another oxygen atom, and react to form carbon dioxide. So that's kind of a inherent time scale limitation of simulation, but overall a good sign that we are getting the chemistry right. So for some new chemistries that we're looking at in the lab currently at NASA Langley, we can look at TGA mass spec, an experimental technique which also is able to record the types of gases that are being released from your sample as it's being subjected to high temperatures. And that's a way, again, to nicely compare directly between experiment and simulation to make sure that there's another way to validate it. So another way to kind of do a simulated version of an experimental technique is to run simulated X-ray diffraction patterns on our models. So these black and gray curves over here show the simulated XRD patterns for kind of the default method, the default protocol. You can see that these peaks are rather broad, which again is characteristic of amorphous carbon, of these glassy carbon materials. This blue peak here is when I increase the annealing time by 3. So increase the duration 3 times, and you see a considerably sharper peak, which corresponds to the 002 peak in the XRD pattern, which is the space between graphitic planes. So in other words, these models are slowly getting more and more graphite-like as you increase the annealing time, which is to be expected. But taking a look at these curves can tell you exactly how far we're getting with respect to experimental samples. So the last one I'd like to take a look at here is a simulated version of HRTEM, of high-resolution TEM images. On the left is a simulated version of one of our chemistries. And on the right is some very nice work by these folks here who looked at glassy carbon subjected to various temperatures and saw how that affected the morphology of that carbon. So if you look at the far rightmost column, you can see notably an increase in the amount of kind of small crystallites that are being formed, which are characterized by kind of these small parallel regions, lines that you can see in these TEM images. And that is small, basically the kind of nucleating bits of graphite that would then increase and grow with more time or higher temperatures. So this is another way to kind of confirm exactly where we stand with respect to comparing our experimental samples with our simulated version. And you can see here that it most closely, our simulated version most closely resembles the lower temperatures on the experimental side of around 600 degrees C. So overall, it's a promising method to predict the important value of char yield without needing any prior knowledge, without making any assumptions, or without interpolating from data from the literature, which is very important because a lot of the kind of interesting outlying high char yield materials are difficult to interpolate. we validated it on a number of different materials, including low, medium, and high charlyl resins and various resin chemistries with various types of various amounts of heteroatoms or non-carbon atoms. In addition, the nice thing about atomistic models is that you can, once you have your final model, you can do additional testing on it, such as looking at the outgassing products and mechanical properties. And so we're currently using this model to look at new chemistries here at NASA Langley and kind of guide experimentalists to hopefully design the next generation of heat shield materials. And before I finish up, I'd just like to mention that I'll be starting my independent research career this fall as an assistant professor at Stevens Institute of Technology. So if you're interested in this type of work, certainly please reach out to me and perhaps we can start a collaboration going. So thank you for your time, and I'd be happy to take any questions.
Thanks for that presentation. So are there any questions? We got a few minutes before the next speaker. Yeah, Taylor.
Is your model able to predict the state of the pore network after pyrolysis in any way, or is that a different size scale?
It is, yeah. So typically, I mean, the pores which would be of interest, for example, for mechanical properties or even transport properties, are beyond the length scale typically reachable by these atomistic simulations. So, so we are looking at, there's actually a tool at NASA Glenn called MatGMC, which kind of takes these lower level simulations and scales them up to mesoscale to larger scale properties of materials, and those can kind of incorporate the larger pores and things like that. So we're working on ways to couple the two length scales, but at my scale, you really can't look at large scale pore networks.
And then we have another one. So whoever has your hand raised.
Yeah, Arnaud Beck from the University of Ottawa. Just a quick question, because you do these atomistic simulations that are on the picosecond timescale. Have you seen data in the literature on ultra-fast laser interaction with these type of materials? And you may be able to validate your model that at shorter timescales. I work with ultra-fast lasers, that's why I ask.
Okay, yeah, that's very interesting. So I mean, I am aware of, like, flash graphitization and things like that you can do with these lasers. We haven't gone that route. We've been doing mostly the TGA, that sort of route. But I would be, yeah, any information you have about that, I'd be interested to hear about. So maybe you can, if you wouldn't mind, yeah, reaching out afterward.
Sure.
I'd be interested to hear about that. Yeah, thank you.
Thanks.
And then I actually just had a quick question before we go to the next speaker. I might have missed this, but what models are you using? Molecular dynamics or some other modeling platform?
Yeah, it's all molecular dynamics. And specifically, it's a reactive force field called ReaxFF, which is able to handle some of the more complex, chemical changes that happen at these high temperatures.
Okay, thank you.
Thank you very much.
All right, so our next speaker is a research officer at the NRC within the Flight Research Laboratory, and they'll be Awantha Jayasiri. We'll be discussing the topic of multi-sensor-based mapping and odometry from full-scale helicopters.
Awantha, if you're talking, you need to unmute.
It looks like there might be some latency issues with the Flight Research Lab right now. So maybe we can move on to our second NASA speaker and give Awantha a chance to rejoin.
Okay, yeah, that's no problem. So Aaron B. Vaughn from NASA Langley Research Center, we'll have him come on up and discuss his data collection preparation for NASA's Quest X-59 mission.
Okay.
Can you guys
Yeah.
hear me or, see my presentation?
Yeah, we can hear you now. We can keep to the order and you can go ahead and present if your screen's going to work.
Yeah, so
Yeah, we're seeing your screen now.
okay. So the initial hiccups actually, I'm not sure what that has happened. So my name is Awantha Jayasiri and I'm an associate research officer in Flight Research Lab, and I've been here about 4 years now. So and I've been involved with developing the perception and navigation modules for a full-scale helicopter. So the work I'm currently going to present is, based on the project that I'm currently, involved with the academia to develop the perception and, develop a platform agnostic multi-sensor parallel system, which can be used as a part of the perception module for the full-scale helicopter. So I'm trying to give a kind of a high-level summary for the project which has been done for a couple of years, and yeah, so okay, so the presentation is working, right? Can you guys hear me?
Yeah,
Hello?
it's a little bit laggy.
Okay, so should I?
Maybe turn your camera off and we'll see if that improves it.
Yeah. Yep, sorry about that. Let me see. Hello.
So it looks like we're having some internet issues with Awantha. So Aaron, if you just want to go ahead and start your presentation, and then we'll come back to him later. Sorry about that, guys.
Okay. Okay, are you seeing my slides?
Yep.
Excellent. Okay. So my name's Aaron Vaughn at NASA Langley Research Center, and I'll be talking about the Quest mission with the X-59, specifically talking about some of our data collection preparation efforts. And, I'd like to thank the colleagues that have helped me with this work, and note that this work supports the Commercial Supersonic Technology Project here at NASA. So the goal here is to, improve our aviation time by decreasing the travel time that we face as we travel. Supersonic flight has the potential to cut your travel time in half when imagine traveling from New York to LA in about 3 hours. That's pretty amazing if you ask me. But sonic booms, unfortunately, are produced continuously as an object goes supersonically, which impacts all of the communities over which a aircraft flies over. And so this year we note the 50-year anniversary of the 1973 ban by the FAA on overland commercial supersonic flight, which annoyance to sonic booms is a significant contributing factor. And so right now, NASA is building an experimental aircraft, the X-59, to demonstrate quite supersonic flight and to collect community response data to inform regulators in their decisions regarding replacing the current ban on overland commercial supersonic flight with permissible noise standards. So how does the X-59 reduce sonic booms? The shape of the aircraft is the key. So the shape of the aircraft dictates how the shocks interact with each other. And so here we have a waveform, a pressure waveform of a conventional sonic boom shown in red, and which is produced by aircraft such as the Concorde, which was a commercial supersonic aircraft from the 1970s to early 2000s. It was limited to flying over the ocean supersonically because of the sonic boom that it would produce. So that waveform that it would produce is shown in red, whereas the shaped boom waveform is shown in blue that is expected to be produced by the X-59, which is also designed to be typical of future supersonic airliners. So again, the shape of the aircraft dictates how the shocks interact with each other. And then the waveform shape here, you can see specifically the peak will make it sound very differently. So the lower peak means that's going to be a lot quieter. You're reducing that peak energy and spreading over slightly more time. And that's going to reduce the sonic boom to a sonic thump. So the Quest mission itself consists of 3 phases: the aircraft development, phase 2 acoustic validation, phase 3 community response testing, all centered around the X-59. So building it, testing it, and gathering community response data with it. So we're still in the first phase with building the aircraft. It is being built under contract with Lockheed Martin. Some details about the aircraft is that it's about 30 meters long. Over a third of its length is the nose, which actually means that there's not a forward-facing canopy. It relies on external visioning system using cameras to display a forward-facing view for the pilot. The wingspan is about 9 meters, and cruise conditions are at 55,000 feet and Mach 1.4. And so it also has an adapted F414 engine for the aircraft to be able to achieve the supersonic speeds. As we move to phase 2, we'll be validating the acoustic predictions of the aircraft. We're going to be collecting data both near the aircraft and on the ground. We want to make sure that we can validate the models of that we've developed. So we have a CFD image here on the left-hand side that shows how those shocks and the pressure is going to extend from the aircraft as it travels supersonically. And we also want to take this time to prepare for our future community tests. So we also want to, we'll have ground microphones and we will be conducting all of these tests over the supersonic test range in Southern California near NASA Armstrong Flight Research Center, as well as which is co-located with Edwards Air Force Base. We want to make sure that the aircraft is safe, which is also part of phase 1, make sure it's safe before we fly it. But then once we are testing it, we want to make sure it's safe. That's not going to have any adverse effect on communities as we fly over it, that the levels are as we predict. And also that, as I said, the commercial supersonic technology that we're producing, the quiet supersonic technology, performs as designed. So just how quiet will the X-59 be? In terms of the sound thermometer we have pictured here, we have the unit of perceived level, which is a candidate metric in units of decibels for human response to sonic booms. And so it's designed, the X-59 is designed to be about 75 dB, and it's meant to be typical of future supersonic airliners as well. And this is comparable to the sound of a car door slamming down at the street or the sound of distant thunder. So something that you'll probably hear, but it's not something that should startle or alarm you or anything. This contrasts with the conventional sonic booms produced by the Concorde, which is on the order of 105 decibels, which is more like the sound of nearby clap of thunder or a car door slamming in front of your face, which can be quite startling if you're not expecting that. So the X59, it's designed to be at safe levels that will not do any harm other than potential annoyance, and we can adjust its trim and its cruise altitudes so that we can vary the level slightly, but typically in this 70 to 80 decibel range is what it's targeted for. So after we validate the acoustics and the aircraft is all ready to go, we'll move on to phase 3, community testing, and we'll be collecting human perception of the aircraft. So the X59 will fly over a community up to 6 times a day for about a period of a month. A month allows participants to have enough time to get, adjust to the sounds and habituate potentially to what it would be like to have supersonic aircraft flying regularly over a community. The annoyance response is captured via a survey that's going to be sent to folks on their, it's going to be an application-based survey that they'll get a little reminder right after a flyover event, and they'll respond how annoyed they are on a scale ranging from not at all to extremely. So this constitutes their annoyance response. And then for each individual flyover event, we will also assign them a noise dose, which is essentially the sound level, how loud that flyover event was. And this is going to be assigned to each participant based on their location, which we'll gather from that survey. And the levels are going to be assigned based off of ground-based microphone measurements that are going to be in the field. We're not going to be placing a microphone at each individual participant's location. We're not going to have a microphone on their shoulder. That would be the most accurate, but that's not the case here, as we're going to have upwards of 1,000 participants in each community. And so we're going to have the disperse of ground microphones throughout the community to get the actual levels measured on the ground, as well as utilize the physics-based modeling predictions to be able to create a sound map to be able to assign each participant their unique noise dose. So we have this annoyance response noise dose, and the relationship between those is the key output that we want to achieve here to be able to figure out how do people respond to these quieter supersonic flyover events. And that information will be fed to the regulators that will then make those decisions regarding the future of commercial supersonic technology. We want the data that we collect to be nationally representative. So the X59 will be flying over 5 communities across the United States, starting in 2025. Each test, as I said, will be about 1 month, and there'll be upwards of 1,000 participants or so in each community that will be recruited and respond to multiple events each day for the period of about a month. The locations are not determined yet, but we want to span various geographic regions, climate zones, urbanicity, and demographics to make sure that we have nationally representative data. This map shows the U.S. climate zones and depicts about 4 dozen candidate airfields. These airfields meet the basic requirements for the X59 to have a long enough runway and all the other various safety constraints that we want to put on it, so we have as much safety as possible in carrying out these tests. And the first test has been decided that it will be conducted out of Armstrong Flight Research Center in Southern California, though the community over which it will fly over is yet to be determined. So we've identified some potential challenges as we're preparing for data collection with the X59. We have conducted previous risk reductions or flight tests with an F-18 performing a low boom dive maneuver over in near Edwards Air Force Base, as well as near Galveston, Texas, where we had a recruited group of participants respond. And with that recent one in Galveston, Texas in 2018, there was 500 participants. We have nearly 5,000 responses for these flyover events, and less than 1% of these responses responded very or extremely annoyed, which is considered highly annoyed, which is the key metric in community noise. And so with very little information regarding what levels people are annoyed at, it's hard for the statistical models to really depict where the annoyance is. And so there's an important balance to strike between not annoying people, but also gathering enough information that we can create models or some sort of relationship between the noise dose and the annoyance response to be able to inform the regulators with their decisions. Another challenge is the potential for variability between communities. We're going to only have the resources to do 5 tests, time and otherwise, to capture the reaction that the citizens of the U.S. have to the sound. And recently we have the FAA that conducted the Neighborhood Environmental Survey, which they surveyed 20 different airports across the U.S. And the annoyance response is shown in the middle in that plot. They vary drastically from one another. And so we only have 5 communities. And if they vary widely from each other, that's going to be difficult to have a single nationally representative dose response relationship for regulators to make their decisions from. And so we're trying to develop some methods to handle the potential different scenarios that you just won't know until you see the data. Also, we want to make sure that we get unbiased data as we inform communities around the nation as we fly over. Before we fly over them, we want to make sure that we communicate clearly what we're doing, but also we don't want to bias people towards wanting supersonic flight, or if people like NASA, we don't want them to say that they're not annoyed just because they want us to potentially succeed. Our success is really collecting that unbiased data, and so we're wanting to make sure we mitigate any bias in our communication by having an expert panel that will review our communication materials as we working with the various communities that would be flying over. And so in summary, we're going to be collecting some dose response data to support new standards for low noise supersonic overflights. The goal of commercial supersonic technology is to decrease our travel time, and we're going to use the X-59 to demonstrate the potential for quiet supersonic flight. And the dose response relationships, that data that we're going to collect, are the focus of these efforts, but particularly in phase 3 of the Quest mission. So thank you for your time. Happy to take any questions.
Hi, I do have a question. Great presentation, by the way. Thank you. So my question is, as far as surveying the noise, is there plans to do a range of sounds, potentially from where the X-59 kind of noise range is going to be up towards, maybe where a supersonic passenger aircraft or something would be?
Yeah, that's a great question. So the X-59 is designed to be at the levels that future, that utilize this type of shaped boom technology should be at. So we will vary the levels. The current predictions are to be about 70 dB to about 87 dB is the range that the X-59 can produce. And so, the Concorde was 105. We're not going to fly an F-18 or another aircraft to reach those levels. One of the previous risk reduction studies did actually have, we had the low boom dive maneuvers that got the lower range, but then inadvertently there's at the same time supersonic overflights that happened. So we had that full range from that data set. Though that data set from Edwards Air Force Base is not necessarily typical of the entire nation, as that group was, generally spouses of military folk that are more more habituated and used to those levels. But yeah, it will have a small range, and that range should cover what the future supersonic airliners should be able to produce. But we won't extend to what the previous ones. There's plenty of data that show that people are annoyed at those levels. Thank you.
That's great. Thanks.
All right, Colleen.
Yeah, I just had a quick question. So once you enter phase 3, how long do you anticipate that community testing is going to take to full completion? Like, when will you have like a final product with the data, if that makes sense?
That's a great question. So recently, some of the timeline has slipped due to the, various factors that have gone into slowing the production of the aircraft and otherwise. So 2025 will be the start of the flight of the community tests. Will be about 2 per year, longer time period between the first and second one. But then I think it was the Cape 14 cycle that we were going to deliver data, but I think it's been pushed back. And so I think 2029 might be the data delivery. But but the timeline has recently changed from what it was. So it's
Okay,
about 2
I
years,
understand.
so 2 or 3 years of data collection, a year of processing, and then delivering it to ICAO and others.
And like the data collection app for the like annoyance and stuff, is that already like in development or is that still need to be built?
Yeah, so we have a contractor team led by HMMH and their subcontractors. I believe Westat are the ones that are doing the survey data collection, and so they've developed an app and they're going to be testing that and doing a mock data collection test to verify that the app works. And yeah.
Okay. Well, I'm excited to see it flying.
Me too. Thank you.
And Jake.
Yeah, great talk. So I had a question. So this X-59 is, of course, designed to hold, 1 or 2 pilots. What kind of challenges do you think will be when you try to scale it up to a commercial airline size?
That's a great question. So yeah, this X-59 will only carry 1 passenger, but the booms it produce are expected to be somewhat typical of the future airliners. They have done some laboratory scale tests or laboratory tests of simulations of the X-59 and different sized aircraft and looking at how people respond. But it's not going to be something that is apples and oranges. It's going to be relatively similar comparison, and so it should scale. And I don't know specifics, but I know that it's something that's been considered in the process. Thank you.
Thank you. Thanks.
All right. So we do have one more question in the chat, but we want to get started with Awantha's presentation again, if we can get it. So maybe you could answer that question in the chat as well. So once again, I'd like to introduce Awantha from the Flight Research Laboratory at the National Research Council of Canada.
Can you guys see my presentation?
Yeah.
Project that I'm currently involved with the academia to develop from agnostic multi-sensor payload system, which can be used as the part of the perception module of the full-scale helicopter. So this is a collaborative project funded by a program called AI for Logistics from NRC to support the objectives of a major project that's the Canadian Vertical Lift Autonomy Demonstration, or the CVLAT. So it's about 5-year duration project with more than 500,000 funding and with more than 6 guys. The visual and inertial information is fused with the LiDAR scans to improve the accuracy of the mapping and state estimation. This provides a better automated solution for the aircraft, even with the absence of the GPS data. So the perception solution also includes the deep learning-based semantic segmentation, object of the identification, and landing zone detection as a submodules. So the multi-sensor perception is achieved by using an architecture called visual inertial LiDAR odometry and mapping. So what you do is you use the sensor information like LiDAR, camera, and IMU and fuse them together to provide position, orientation, and mapping information. So the payload has been designed and manufactured by the university team according to the airworthiness and design guidelines of the Flight Research Lab at NRC, and the data capture is performed using different platforms. So then actually the developed payload is tested on a vibration testing, and the specific mounts is designed to reduce the the vibration at main frequencies. So these are some specifications regarding physical, electrical, and the environmental aspect of the payload. Let's have a look at the solution and the perception solution, for example. It has three main subsystems like VLOM subsystem, place recognition subsystem, and the labeling subsystem. So it represents the improved simultaneous localizing mapping solution. It's a SLAM solution, so it fuses the sales information in a different rate and fuses GPS data while it's available. The loop close is done using visual information with the help of the image database. And that includes the image segmentation and the object detection modules. And also it has a visual aided point cloud segmentation module to select landable and unlandable zones. So if you have a look at a little more, so more of the markets implemented as separate more so so the VLM architecture, the IMU is including the data point global map. Here we use two separate factor graphs, photometry and mapping modules, and the nonlinear optimization is performed using Google Sales Solver. So this is the hardware. The solution that I explained on the slide gets an Xavier GPU. So the collected service in different platforms was processed from pipeline to some.
All right. Unfortunately, it seems like the latency issues are continuing. So I think at this point, we will conclude this presentation. Unfortunately, we weren't able to get through that last one. However, Awantha has told me that he's going to send me a version of his PowerPoint slides that can be shared. So for those with interest in the topic, there'll still be a presentation available to be shared after the fact if you want to either reach out to me or Awantha himself. So I'd like to thank all the speakers again for preparing these presentations, especially at the summertime when it's a great time to be taking vacation. And also I'd like to thank all the attendees, and especially I'd like to thank Jamesa at NASA for spearheading this activity and organizing it from her end.
So yeah, thank you all the participants from NRC, as well as we had a bunch of IFAR members in attendance as well. So yeah, thank you guys again and have a great afternoon /morning / wherever you are in the world.